We are now able to draw Lewis dot structures for any molecule, which tell us a lot about the structure of a molecule. They tell us which atoms are bonded with which other atoms, whether by single, double, or triple bonds, as well as any lone pairs that may be present. They can tell us whether any atoms bear a formal charge and whether there is any resonance. But they have one limitation. They are two-dimensional representations of molecules that in actuality are three-dimensional objects. So we need a way to describe the three-dimensional structure of molecules. This includes the angles between the bonds, as well as the spatial orientation of all the atoms. The model we will use to determine these things is called valence shell electron pair repulsion theory. The central idea of this theory is that the things that surround an atom, whether they are bonds to other atoms or lone pairs, consist of negatively charged electron density, and these areas of electron density will repel each other. This means that the electron domains surrounding an atom will spread out to be as far away from each other as possible. The orientation that these electron domains will adopt, which once again includes both bonds to other atoms and lone pairs, depends on the number of them present. Two objects that are attached to a central atom will find that a 180-degree bond angle is the best way to maximize the distance between them. This will be called a linear electron pair geometry. For 3, it would be 120-degree bond angles. This is a trigonal planar orientation. For 4, we must begin to use the third spatial dimension, so it won't be 90-degree bond angles. If 4 domains adopt a tetrahedral geometry, there will be 109.5-degree bond angles, which is substantially larger than 90. For 5, we get the trigonal bipyramidal geometry, which has both 90-degree and 120-degree bond angles. And for 6, we get something called an octahedral geometry, with all 90-degree angles. This would be the geometry of that SF6 molecule we were looking at earlier, which means the flat representation of the Lewis dot structure is not representative of the real molecule in terms of the actual spatial distribution of the atoms. This table summarizes the geometries that are dictated by the number of electron domains that surround a central atom. But these larger categories can be split up into subcategories if some of the electron domains are lone pairs. So we still have much to learn about valence shell electron pair repulsion theory.